All right, so we begin the final exam review with Unit 1 number sense. And so what number sense was is saying, well, if I give you different types of integers and different types of mathematical operations or different signs, how do we handle those sorts of situations? So starting off with number 1 here, integer operations. Well, integer operations revolve around saying, well, what if we add, subtract, multiply, and divide different types of integers, whether they be positive or negative. So in the first example here, we see that negative 5 plus 4, well, a negative plus a positive 4, that's going to result in some either positive or negative integer. And now we need to realize negative 5 is going to be a greater number than positive 4. So the negatives outweigh the positives. And so I should get an answer of negative 1 here. Now, if I move on to B, I have negative 2 plus a negative. A positive and a negative, when they're compared next to each other like this, a positive and a negative, that is ultimately going to be a negative. So it's technically negative 2 minus 5, and that is negative 7. Negative 4 minus 3, well, negative 4, and we remove even more numbers or subtract even more integers away, that's going to also be negative 7. And then we have negative 8 minus minus. As soon as you see this double negative like this, you're thinking, okay, I got to transform that to be a positive. So you could actually write a positive directly over top, or just write an arrow like this and say that becomes a positive. And so negative 8 plus 12, well, now the positives outweigh the negatives, and I get 4. Okay, we shift to E. Negative 4 times a negative 11. Well, remember, anytime we have this double negative situation, it becomes a positive, and double negatives, negative 4 times a negative 11, will become 44. Negative 9 times 6, well, a negative times a positive is ultimately going to become a negative, and therefore I should get negative 54 here. All right, 6 times 5 will give me positive 30 because we have two positives, therefore this should stay positive. 17 times a negative 2, well, if we see this positive and a negative come together, that should ultimately become a negative, so our answer will be a negative. And now we can go 2 times 10, which is 20, 2 times 7, which is 14, and so we therefore should get negative 34 for this solution here. All right, negative 16 divided by a negative 4, negative and a negative, that's going to become a positive. Negative is a positive, so 16 divided by 4 is 4. 9 divided by a negative 3, the positive and a negative are going to come together to make a negative, and I get negative 3. Negative 48 divided by a positive 4, well, if I have a negative and a positive, this is going to become a negative, and so my answer will be negative, and 48 divided by 4 is 12. And then lastly, a positive divided by a positive, or 12 divided by 6, will ultimately give me 2. All right, now we want to convert mixed and improper fractions either to an improper fraction or a mixed fraction, depending on what they're asking for. So if we want to convert this mixed fraction, 3 1/5, to an improper fraction, here's the algorithm that we can kind of follow in order to make this an improper fraction. Suppose we have some x to the y over z. Well, in order to convert this into an improper fraction, or this mixed fraction into an improper, what we have to do is multiply x times z and then add the numerator, and that becomes whatever's in the numerator all over whatever was in the denominator originally. So it's going to be the coefficient number times the denominator, or this number times this number, and then add these two to get my numerator, and then just leave the denominator. So in the example below here, when we want to do this, we're going to go to make our numerator, it's going to be 3 times 5. We're going to add that number that was currently in the numerator and leave our denominator of 5. This becomes 3 times 5, which is 15 plus 1. That's 16 over 5. Now, you're always thinking, can I reduce this? In this case, no, you can't reduce this because 5 is actually a prime number, or something that can only be divided by itself, or 1. All right, let's do the same thing with the next one. 2 times the denominator, which is 4, plus our numerator all over what it was already in that denominator. 2 times 4 is going to be equal to 8, plus 3 is equal to 11 over 4. Yet again, this can't be reduced because 11 is actually a prime number. 11 can only be divided by itself, or 1. Now, in the opposite case, what if we want to take something that's an improper fraction, or something like 11 over 3 or 15 over 7, because there's a greater number in the numerator than there is in the denominator? What we're going to do is we're going to say, okay, if we want to take this improper fraction, 11 over 3 or 15 over 7, and move it into a mixed fraction, or something with a coefficient term out front here, or a certain amount of whole numbers, what we have to be thinking is, if I see that it's out of 3, then I need to be thinking, how many times can I put 3 into 11 evenly before I have to start breaking it apart? Well, 3 can be multiplied into 11 3 times, because we know that 3 can be multiplied up to 9. But if we go any more, then we're going to get to 12. And here's what I mean by that. What if I take multiples of 3? Well, I can go 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. Do we see how we hit this number that's greater than what's in our numerator? That means we've gone too far. So we go back to the one that was previously under that number, or under the number in the numerator, and we say, okay, how many times did I have to multiply my denominator to get there? Well, I need to multiply it by 2, and then by 3. So how many times can I put this number in? Well, it's by 3. So we're going to have a 3 coefficient with how many, if I multiply to get to 9, well, if I'm at 9 and there's a total of 11 units, that means there's a difference of 2. And so I'm going to put 2 in my numerator here and over that same denominator. There we go. There's our mixed fraction. Okay, let's do the same thing with the next one below. If I want to say, how many times does 7 go into 15? Well, I'm going to start by doing multiples of 7. And I'm going to do that below here. 7 times 1 is 7. 7 times 2 is 14. 7 times 3 is 21. Whoops, we've gone too far. 21 is greater than 15. So we have to backpedal, and we have to go back one and say, okay, well, 14 is definitely less than 15. And how many times did I have to multiply to get to there? Well, it was times 1 here. To get to here, it was times 2. So we have 2 whole units. And if I allocated 14 of the 15 total units, that means I have 1 more unit out of 7. Because the denominator will always stay the same, but if I've allocated 14 units with this 2, or 2 whole amounts, then I only have 1 left out of the 15 to allocate. All right, now, order of operations, this one's a really big one. BEDMAS, as we followed through number sense, or in our number sense unit, brackets, exponents, division, multiplication, addition, subtraction. So what we're going to have to do with this problem here is we're going to first start with our brackets. We're going to simplify the interior of each of the brackets. So I'm going to start with this one here. 32 minus 30 is equal to 2, and I'm going to leave that exponent of 3, minus 2 plus 1/2, because none of those terms deal with brackets. Now I'm going to simplify this bracket here. 18 divided by 3 is equal to 6. And 6 times 5 is going to be equal to 30. So the bracket here should be equal to 30. And this is all over. Now I have to go to the denominator here and look at these brackets. Root 49, or the square root of 49, that's equal to 7. And 7 minus 2 squared is 4. We could rewrite this instead, 7 minus 4, which is equal to 3 in the denominator here. Okay, now we go on to our next step here, and I should be putting equal signs because I'm simplifying this now in each step. Now, according to BEDMAS, we deal with the exponents. 2 to the 3rd power, that's like writing 2 times 2 times 2. We could actually write that even above here, 2 times 2 times 2, which we also know is equal to 8, minus 2 plus. Now, in the order of operations, we dealt with our brackets. We then dealt with the exponent term, which was 2 to the 3. Now we can deal with our division and multiplication. So what I'm going to do is multiply this 1/2 times 30. Well, 30 divided by 2 is equal to 15. And this is going to be all over 3. Now I'm going to simplify the numerator. So I'm going to combine terms that I can combine. 8 minus 2 is equal to 6. And 6 plus 15 is equal to 21. And this is going to be divided by 3. Finally, 21 divided by 3 is equal to 7. So when we do these order of operations, we're simplifying these things that look quite complex right off the top here. Well, they should typically reduce down to some form of simplified fraction or just some sort of integer, and it could be positive or negative. In this case, it was positive, but in other examples, it may be negative. And you may only be able to reduce it down to something like a fraction, but in this case, we know that 21 over 3 reduces to a 7, so we're going to reduce that as much as possible. And if you're given this type of problem, I would always reduce it if possible. I would break it down to the simplest form that you can. So if it's going to reduce down to only a reduced fraction, do that. If it's going to reduce down to some form of positive or negative integer, make sure it's in that form. All right, so now we're going to deal with prime factors, greatest common factors, and lowest common multiples, or what we've talked about a lot through the year are GCFs, which are greatest common factor, and our LCM, or our lowest common multiples. Okay, we're going to deal with two different examples here. Determine the prime factors of 390 and 210. Okay, so what I'm going to do is I'm going to first start with doing my factor tree, 390 and then 210. Well, on both of these, what we can actually do is we can say, because they end in 0, why not just divide by 10? That's going to make our job pretty simple here. 39 and 10. And then we're going to break 10 into 2 times 5. Well, 2 and 5 are both prime numbers, so we can't continue that trend. Now we have to go to our next branch here, and we say, well, 39 can be divided by 3, which breaks this into 3 and 13. Okay, now we stop here because 3 and 13, 2 and 5, they're all prime numbers. We can't break them apart anymore, so we're going to stop. We go to 210 now, and we say, okay, well, if we divide this by 10, it becomes 21 and 10. 10 will break into 2 and 5 again, and 21 can break into 3 and 7. Now we stop there on that one because we know that those are all prime numbers. Once you hit the prime numbers, this is what I would recommend. You highlight that bottom row or circle those numbers. When you get to the bottom of these trees, you should be circling or highlighting just to make sure that you're tracking all the prime factors that make up the number. Okay, next step, what I would recommend is going 390 is equal to the product of all those prime factors. 3 times 13 times 2 times 5. This is a really important step to do because we know that the product or the multiplication of all those prime numbers at the bottom of these trees are equal to that number. Again, we're going to go 210 is equal to 3 times 2 times 5 times 7. Now, what might be also a good idea is to put them in numeric order or least to greatest. So if I was to go back in both these tables, what I could do is put them least to greatest, and that's going to actually help us with our LCM and GCF. So from 390, we start with a 2, then we go to a 3, then we go to a 5, then we go to 13. In 210, we start with a 2, then we go to a 3, then a 5, then a 7. Okay, now they're in numeric order, and you're going to see why this helps us. When we talk about our GCF is equal to, well, here's an easy way to remember how to do GCF and LCMs. F representing the fewest of the shared. This is the fewest of the shared. Now, if I look at these two lists here of the prime factors, well, if I'm looking for the fewest shared, well, I'm going to start with the 2's. The fewest amount of 2's shared is 1, 2. So in my list, I'm going to put 2 to start. Then I'm going to go to the 3's and say, okay, well, when I look at the list of the shared 3's, there's at least, or the fewest amount is 1, 3. Then I'm going to go to my 5's and say, well, of the 5's that are shared, the greatest or the least amount, is 1, 5. And then finally, we look at the last numbers here. 13's not shared, 7's not shared, and so we can't include this in the list of our GCF. Now, the final step for the GCF is to say, okay, well, 2 times 3 is 6, times 5 is equal to 30. So that is our greatest common factor, or the number that is the greatest multiple of both of these two numbers. Okay, now we're going to look at our LCM. LCM below. Here's an easy way to remember it. We're going to underline the M and say it's the most, regardless of shared. So it's the most, and they do not have to be shared. So when I look at both these lists here, I'm going to look at the 2's. What is the most amount of 2's regardless of shared? Well, it is 1. So we have 2 times. I then go to the 3's. What is the most amount of 3s regardless of the list? Well, it's 1, 3 times, I look at the most amount of 5s, which again would be 1. The most amount of, in this case, 7s, most amount of 7s regardless of list, they don't have to be shared, is 1, 7. Multiplied by the most amount of 13s regardless of the list, because it doesn't have to be shared, that would also be just 1, 13. Okay, so now if I multiply these numbers all together, I'm going to go 2 times 3 times 5 times 7 times 13, and that's going to give me an answer of 2730. Okay, now what does the LCM actually represent? Well, if I was to multiply these numbers out a bunch of times, so suppose I was to do this off to the side, I go 390, and then 390 times 2, which would give me some number, and then times 3, which would give me some number. Well, the first number that both of these would reach, when I do that, when I do multiples of those numbers, so I'm going to go times 3 and continue on, the first number when multiplying both 390 and 210 outwards would give me 2730. That's the first number that when I multiply those numbers by 2, by 3, by 4, that's the first number that both of them reach. Okay, now let's go into example B here. Determine the prime factors of 32, 40, and 48. So we're going to need to make a quick correction in our notes here because of the one that was handed out to you, this is the same error. We're going to convert this number to 40 here and this number to 48. And we're going to do the same thing with here, 40 and 48, just because there was a little bit of a typo there. So it starts with 32, 40, and 48, but then in your notes it goes to 48 and 50. That would make no sense here. Okay, let's determine the prime factors of these three numbers here. We have 30, 40, and 48. We're going to break them apart into their factor trees or their prime factor trees. So because it ends in 0, I'm going to divide it by 10. 3 times 10 gives me 30. I split this into 2 times 5. 40 I can split into 40 and 10, which goes to, or 4 and 10, my apologies, which goes to 2 and 5. 4 can split into 2 and 2. 48, I'm going to move this over just slightly. It doesn't end in 10, or it doesn't end in 0, so I can't divide it by 10. So what I'm going to do is I'm going to divide this by 4, which will give me 12. And then I'm going to split this into 2 and 2, 12 into 3 and 4, and then I'm going to have 2 and 2 from there. Now, this is where I'm talking about highlighting becoming really important because we want to highlight all the prime factors at the bottom of each of these trees here. So I'm going to go along and highlight each of them. And then what I'm going to do is I'm going to go off to the side and put them as a list of those prime factors or the product of those prime factors. So 30 is equal to 2 times 3 times 5. I just put them in numeric order or ascending order from least to greatest. Now I'm going to go to 40, which is equal to, if I have 3 2's as follows here, I have 3 2's. I'm going to group them together using our exponent knowledge. 2 to the third power, because there's 3 2's, times 5. And then finally, I'm going to go to 48 and say, well, 48 was split into 2 times 2 times 3 times 2 times 2. How many 2's do I have? Well, I have 2 here and 2 here, meaning that I have 4 2's, and it's multiplied by my 1 3. All right, let's use these lists of prime factors in order to find our GCF and LCM. The GCF, remember, GCF is the fewest that are shared. So it must be shared amongst all 3 of those lists. So when I look for the fewest amount of 2's, well, the fewest amount of 2's occurs in that first list of prime factors from 30, and that is 2 to the 1. So I'm just going to put 2 here. Now, I want to go on to my 3's. Are 3's shared amongst all the list? No, because it doesn't appear in the middle list. There is no 3 here, so I can't consider that for my GCF. And then I look at the 5's. Well, there's 5's here, but there's no 5 in the bottom row here, so it wouldn't be appropriate to include that in the GCF. Therefore, my GCF, or the greatest common factor for this list, is going to be equal to just simply 2. So I'm going to backpedal there. Okay. The LCM. The LCM here. Let's erase that. LCM. Okay, I'm going to underline the M representing the most. but they do not have to be shared. Similarly, what we put above, they do not have to be shared. So for my LCM, I'm going to look between the lists here. The most amount of 2's regardless of list, that is 2 to the 4, times the most amount of 3's regardless of the list. Well, there's only one 3 that is the most. And then times the most amount of 5's. Well, there's only one 5 in each of the first two lists. So there we go. Now, if we go 2 to the 4, we know 2 to the 4 can actually be written as 2 times 2 times 2 times 2. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. 16 times 3, well, if we do 16 times 3, we're going to get 48. And then 48 times 5 will give us a solution of 240. So our number here is equal to 240. So GCF, which is our greatest common factor, is 2. LCM, or the first number that 30, 40, and 48 all multiply to, give us 240. All right, now adding, subtracting, multiplying, and dividing fractions, what I would recommend is if they don't share the same fraction, what we should do is make sure that these are in terms of an improper fraction and then see if we can add or subtract them here. So what I'm going to do here, I'm going to convert these both to improper fractions from them being mixed. So for my first fraction, it's going to be 2 times 5 plus 2. That's 10 plus 2 is 12 over 5 minus 1 times 4 is 4 plus 1 is 5 over 4. Now, here comes the LCM terminology. If I'm looking at the denominator and I want to create a common denominator, I need to use LCMs. So what I can do here is I can say, well, the LCM of these two denominators is equal to 20. The first number that 5 and 4 both multiply to is 20. So in order to create an LCM here, or the multiple that would be for a common denominator, I'm going to multiply my first fraction by 4 over 4. And I'm going to multiply my second fraction by 5 over 5. Okay, that means I'm going to have 4 times 12, which is 48, over 20, minus 5 times 5, which is 25, over 20. Okay, now I can reduce this a little bit, and I'll maybe do that in the next step below here. 48 minus 25, that's going to be equal to 23 over 20. And 23 is actually a prime number, so I can't reduce this anymore. We are done right there. Now, depending on what they wanted, so if we look back at the instructions here, adding, subtracting, and dividing mixed fractions, they may ask us, oh, well, if we want to convert this from an improper fraction back to a mixed fraction, what would we do? Well, yet again, how many times can 20, or sorry, my apologies, how many times can, 20 go into 23? One time. What is the remainder? Well, if I've allocated 20 of the 23 units, that means I have 3 out of 20 remaining. So there's two ways to write that answer. We could have 23 over 20, which is the improper fraction, or we could put it as a mixed fraction with 1 and 3/20. All right, now, if I go off to my second example here, I'm going to do the same thing that I've done before. I'm going to convert them to impropers, and then we can maybe convert them back to mixed if we wanted to in the end. So what I'm going to do with these is I'm going to say 4 times 5 is 20 plus 4 is 24 over 5 times. Now, we have 1 times 7 plus 3. That's going to be equal to 10 over 7. Now, if we're multiplying fractions, we do not have to create an LCM, because what happens is when we're multiplying, we're actually just multiplying directly across numerator to numerator and multiplying across denominator to denominator. So this is going to become equal to 240 over, in this case, 5 times 7, which is 35. And now, if we reduce this as a fraction, we can actually reduce this just a little bit. And this is going to be equal to 48 over 7 as a reduced fraction. And then if I wanted to convert this into a mixed fraction, well, what I can do here is I can say, how many times does 7 go into 48 evenly before I have any remaining? Well, off to the side, what you could do is this. 7 times 1 is 7, 7 times 2 is 14, 7 times 3 is 21, 7 times 4 is going to be equal to 28, 7 times, and you could continue this pattern on and on and on. And then eventually what you're going to do is you're going to reach, well, in this case, if we can, okay, so if we want to convert this from an improper fraction to mixed, well, I can do 7 times 1, 7 times 2, on and on and on. Eventually, I'm going to reach 7 times 6, which is equal to 42. I have one more after this, which would give me equal to 7 times 7, which would give me 49. But 49 is greater than the numerator, so I have to backpedal and go, oh, well, this is multiplying by 6 to get to 42. So I have 6 whole units. How many do I have remaining out of the 48 to allocate? Well, I would have 6 units and the denominator stays the same. So we have our improper fraction and our mixed fraction there available. All right, let's go down to the bottom one here. Same thing we're going to do. 3 times 3 plus 1, that's 9 plus 1 is 10 over 3, plus 4 times 8 is 32 plus 3 is 35, all over, in this case, 8. Okay, the LCM here, because we are adding these two, we have to create an LCM here. So if I add these two fractions together, I have to make sure they have their common denominator. The common denominator here would be equal to, in this case, 24. So what I'm going to do is I'm going to multiply my first fraction by 8 over 8. And I'm going to multiply my second fraction by 3 over 3. So this is going to be equal to 8 times 10 is 80 over 24. And then plus 3 times 35. Well, 3 times 30 is going to be equal to 90. And 3 times 5 is 15. So 15 plus 90 is 105. And this is going to be over 24. If I add these things together, I'm going to get 185 over 24. And then 185 over 24, it won't reduce anymore. You're not going to get a simpler fraction out of this. But what we could do is convert this into some form of mixed fraction if they asked us to do that. And as a mixed fraction, what we could do is similar to what we did before. We could multiply out 24 a bunch of times, 48, and we could continue on and on and on, and we would get some number. And then with that multiple, we would find that the number of times that 24 can fit into 185 evenly is going to be 7. How many would we have remaining at that point? It's going to be 17 over 24, or there'll be 17 units remaining once we get to that multiple of 7. So we have our improper fraction and our mixed fraction. Okay, and then when we look at this example here, we have division instead between the two. So I'm going to start by converting these mixed radicals into improper. So 3 times 3 is 9 plus 2 is 11 over 3 divided by, and then we have 2 times 6, which is 12, plus 1, which is 13 over 6. I'm going to use something called the reciprocal and convert this from division to multiplication. 11 over 3 multiplied by, I'm going to flip that fraction using the reciprocal. I'm converting division to multiplication. And you may have heard this as the kiss and flip rule, but I'm just going to treat it as anytime you go from division to multiplication, you use the reciprocal of the second fraction. The reciprocal. Okay, now remember in multiplication, we can multiply directly numerator to numerator, denominator to denominator. So this is going to become 66 over 39, which is equal to 22 over 13. And if I wanted to make this in terms of a mixed radical, what I can do is say, well, 13 times 1 is 13, 13 times 2 is 26. Whoop, gone too far. 26 is greater than our numerator of 22, meaning I can have one full unit. And then if I've allocated 13 of the total 22 units, how many do I have left over? I have 9 of the 13 left over, or 9 out of 13. All right, roots, radicals, and estimating values. We want to estimate some roots here. So in order to estimate roots, what we're going to do is use perfect squares that are near that number in order to help us here. So if I want to estimate this, well, the perfect square that is below 10 is going to be equal to, because we want to write it like this, root 10 is going to be less than some number and greater than some number. If I put a perfect square that's less than 10, we know perfect square less than 10 is 9, and a perfect square that's greater than 10 is 16. Okay, so square root of 9 is 3, which is less than the square root of 10. But 10, or the square root of 10, is less than the square root of 16, which is 4. Now we want to say, what is the number, or what is 10 closer to? Is it 16 or is it 9? Is 10 closer to this number? Or is 10 closer to this number? Well, we would say that because 10 is only within 1 of 9, it's going to be closer to that. So by estimation, square root of 10 should be approximately equal to something like 3.1 or even something like 3.2. Just purely based on an approximation of 10 being closer to 9 than 10 being closer to 16. We know 10 is closer to 9 and the square root of 9 was 3. So we're going to say it's something around 3.1 or 3.2. That would be a very good guess in here. Now, what we're going to do is we're going to do the same approximation method below here. So we're going to go square root of 220 is going to be less than some square root but greater than some other square root. All right, so a perfect square root that's less than 220 would be square root of 196. And then a square root that's greater than 220 would be square root of 225. Okay, so now if I want to think about these, well, square root of 196 is equal to 14, which is less than the square root of 220. But the square root of 220 is less than the square root of 225, which is equal to 15. Now we're thinking, okay, which number is 220 closer to? Was 220 closer to 196 or is it closer to 225? Well, I would argue it's significantly closer to 225 than it is 196. So we can say, therefore, the square root of 220 should be roughly equal to something like 14 and because it's closer to 15 than it is to the 14, we're going to say maybe like something like 14.8 or even 14.9. Those would be very good guesses in this case for those solutions. All right, place the following numbers in order from smallest to largest. Do not use a calculator. Well, here's what we can do. We can convert them all into entire radicals. And if I make them all entire radicals, that means I'm bringing everything entirely under the radical. Here's how I do that. If I look at the first number here, 2 root 5, well, 2 root 5, if I want to bring the number back under the radical, I have to square it because we had to square root the number to bring it out. So now I have to square it to bring it back in. This is 2 squared times 5. That's equal to 2 squared is 4 times 5 is root 20. Okay, now I go to the next one here. We bring it back under the radical. That's 4 squared times 3. 4 squared is 16, and then 16 times 3 is 48. So we're going to have a larger number there. And then if I want to bring the number back under, I have to square it times 4. We have 9 times 4. 9 times 4 should give me equal to 36. And then finally, I'm going to bring this one off to the side here and say, okay, well, if I bring the 5 back under, it's 5 squared times 2. 5 squared times 2 is going to be equal to 25 times 2. That is square root 50. Now, what we know about radicals is that the smaller the number, in terms of integer numbers, the smaller the number, the less it's going to be. So what we can say is in order from smallest to largest, according to the instruction here, we know that our smallest is going to be root 20. and I guess we should put the original numbers here. Our smallest is going to be 2 root 5. Our next smallest is 3 root 4. Our next smallest here is going to be 4 root 3. And then lastly, our next smallest is going to be 5 root 2. So therefore, that's our order there. All right, convert root 48 to a mixed radical. These ones are a little bit tricky, especially if you haven't seen them in a while. In order to convert this to a mixed radical, or something on the outside with something under the radicand, or the symbol that makes the root, what we have to do is say, what is the largest perfect square that divides this number evenly? Well, if I look for the largest perfect square that divides 48 evenly, I would realize that this would be equal to 16 times 3. Because 16 times 3 is equal to 48, and that's the largest perfect square that evenly divides 48. And here's another way to indicate that you got the right solution. If your second number, or the multiple number here, is a prime number, or some number that only multiplies by itself, or 1, or can't break down any further, you know that was the largest perfect square, because that won't simplify any further. And here's how we take it the next step. If it's being multiplied like this, we can actually separate them under their own radicals. And therefore, root 16 is 4 multiplied by root 3. We have a perfect square and an irrational number left over. Because square root of 3 would be an irrational number, it doesn't simplify anymore. All right, now if I want to bring the root or the number from the outside back under the radicand, what I have to do is I have to say, or back under the radical, what I have to do is I have to square it like we did in our approximation example. So I'm going to go square root of 4 squared times 5. 4 squared is equal to 16. And then we know 16 times 5 is going to be equal to, in this case, 80. There we go. So simple way of remembering it, a mixed radical is something on the outside, something under the radical, or we have entire radicals, which is everything under the radical. All right, important rules on radicals. Root 16 times root 4, or anything dealing with multiplication and division, they will be equal to everything under the radical entirely. So if we look at this and we say, oh, okay, things are being multiplied, and then we put them under one radical, or 16 times 4, which we know is 64, because this is also equal to square root of 64, we can bring both of our things that make up our radicands under the same radicand and multiply them. Same with division. We can go, this is equal to 36 divided by 4, which is equal to square root of 9. So maybe I should expand that over here as well, as say, we can bring them under the same radical, 16 times 4, which is equal to square root of 64. But this does not work with addition and subtraction. When we deal with radicals like this, it is not appropriate to say square root of 25 minus 16. That is not the right answer. Whereas with multiplication division, we can bring them under the same radical. With addition and subtraction, we cannot do that. So it is not equal. Similarly with addition, I cannot just say it's 25 plus 9 under the same radical and say that's equal to that sum of those numbers. That is not true. So this is not equal, and not equal for subtraction. All right, substitution. Substitution means if I give you a number that represents a variable, and then I give you some equation that involves that variable, well, sub it in and tell me what the value is. So if they tell us that we have this sort of function here, or this sort of equation here, or statement, and then they give us the value of b in that statement, well, let's plug it in. This is going to be equal to 2 times b, which is negative 3 squared, minus 5 times a negative 3 plus 6. Now, do you notice how when I make this substitution for b, it's put in brackets? That is really, really important. Here's why. When I say this is equal to, if I didn't have the brackets here and I wrote this as something like 2 times negative 3 squared, well, we know that this squared doesn't apply to the negative out front. Whereas in our case where we have the brackets in the proper written form, the squared gets applied to the negative. So what you would find is if you don't write those brackets like that, you're actually going to get the opposite sign in some cases. So it's 2 times negative 3 squared. Negative 3 squared is positive 9, and 2 times 9 would be left over, minus negative 5 or minus 5 times negative 3, what happens with this double negative? We have a negative times another negative, or a negative and a negative. We always know this becomes a positive, even right from our first get-go example. So this is plus 15 and then plus 6. All right, so this is going to give us 18 plus 15 plus 6. Well, we know that 10 plus 10 is 20. 5 plus 6 is 11, so that's already 31. And then 31 plus 8 is going to be equal to 39. All right, which of the following expressions are positive? This is a really good example and really important to pay attention to the details here. So when we look at the expressions for being positive, remember, brackets make a huge difference. In the first one, is the squared applied to the negative? No, because it is not surrounded in brackets. So we treat it as this is equal to negative, and then 3 squared is 9. The negative is not attached to the squared. In our second example, though, the negative is attached to the squared. So a negative times negative would become positive, and then 3 squared is 9. 3 squared is just simply equal to 9. If I do negative 2 to the third power, this is like writing negative 2 times negative 2 times negative 2. The first two negatives here are going to become positive, but then a positive times a negative is negative, so we get a negative, and then 2 times 2 times 2 is 8. This is equal to negative 2 to the third power. Remember, if the negative isn't surrounded in the brackets, it's automatically just negative, and then 2 to the third power is 8. 2 to the third power is 8 here. And so when they say which ones are positive, we get a positive for the second one, we get a positive for the third, and then we get a positive for the last one.